Bismillahirrahmanirrahim. Welcome to Easy Learn, and this is the introduction to electronics, episode 11. Before this, we already discussed episode 10 complete, and before going further discussion, and I had decided to summarize all the episode 10s in one episode so that students who joined us right in between the whole series can understand what we already discussed and what we are going to discuss, the plannings and so on, other things. This is the you can say the mid of the series, and at that point I want to recap all the things what we already discussed in the 1 to 10 episode, and we are going to analyze this in a very brief, precisely summarize these things and recap. Let's start from the episode 1. We just try to give a very brief touch to the magnets. What is basically a magnet? A magnet is a material, it is specific material which attracts the ferromagnetic metals or materials. Sometimes it tries to, we can also magnetize other things. Why does it attract? Because its magnetic field of the lines inside the material are particularly aligned up. They have the potential to attract. If we analyze and learn from different if we throw the sand on the paper, we saw in the previous episodes that how a magnet can align the sand into a particular direction, like these magnetic field lines. It looks like this. From that analysis of the sand on the paper, when a bar magnet is placed, we found that there must be magnetic field lines, and the structure is this, and this arrowhead can be used to represent the north, and this tail is used to represent south, as the positive charge in the case of the charges, positive and negative charge, two types of charges. Like charges repel each other, opposite charges attract each other. Same is the case when the north pole is bring closer to another north pole, they are trying to repel, and north pole attracts the south pole. Means to say, this is the representation of graphical representation of north south, and these magnetic fields of the line is trying to connect with the south, and these are why these arrowheads are going out from the north, because these are the like poles never going to attract. These are entering into the south. This is the north and this is the south, so attraction always occurs. This whole area, this is the area where we can experience these magnetic field of the lines, and in this area magnetic field of the lines are used to recognize its efficiency. Here you can see that mostly magnetic, here many magnetic field lines, like 1 2 3 4, rough analysis 4 5 lines here. But if we are going to analyze the same space but another place, you can see only one magnetic field line coming up from here, just for the sake of analysis. This means that here magnetic field lines are different, and it means it has a different intensity here. It is has magnet has maximum power here. It's a field of attraction or repulsion. If we bring a ferromagnetic material here, it will experience more force while as compared to this one. So these shows the intensity, and we cannot divide the north and south pole separately. Like if I cut from the center, it doesn't mean that this one only a north magnet and this will become only a south magnet. The both will then again line up in the north and south. It is not possible to have only a north magnet without south, or it is not possible with south without with only south pole magnet without north. Means to say, both must be attached with each other. It is not possible to have only single type of magnet. The region around a magnet where magnet's effects are experienced, this is the region, and this is called the magnetic field, in like this box, because the magnetic field lines are experienced anywhere in this region, and this is very much important for the sake of analysis. And if it depends upon the magnet, size of the magnet and its intensity, and these magnetic field lines will be more at the south, closer to the north and closer to the south. Magnetic field lines are used to represent basically magnetic fields. So this means that the inside this box, this is all magnetic field, where this magnet has effect on the area, it has control over this box, and this is the jurisdiction of this magnet inside the box. Suppose we have a conductor here, and if we try to connect this with the external source, then it will have an electric field inside the conductor, and the direction of the electric field is the same. If we consider here from positive to negative like conventional current, the direction of the current, following the direction of the current, the electric field also have the same direction as of the current, while the magnetic field direction is perpendicular or normal to the mixed angle of the 90 degree with the current and with the current. Like if the current is flowing here, it has the angle 90 degree. It will be like this. Its direction depends upon the flow of the current. If we change the and reverse the polarity like positive and negative change, then its direction will also be reversed. Intensity of this magnetic field that is developed across the conductor depends upon the type of the material that is conductor made up of and the intensity of the current that is applied. How we can find out the direction? That is very simple. Right hand grip rule. Just use your right hand and tightly grip the magnetic field will indicate by your fingers of the right hand. All you have to do is just put the solenoid or whatever you want to. For example, in our case here we have the this conductor. Put this conductor in your right hand, grip it with your fingers, and your fingers will be indicating the direction of this field. The magnetic field intensity is solenoid is uniform. Inside this solenoid, the magnetic field is uniform, while you can see the outer side it is not uniform. Here it is more, here it is less. What I discussed in the previous slide here, that here it is different, while here it is more stronger magnetic field. While in this solenoid, inside the solenoid the magnetic field is uniform, and mostly a soft iron piece is placed inside it to make it further strong magnetic field. This is electromagnet. Solenoid is basically electromagnet, so we put sometimes a ferromagnetic material like iron, soft iron, so that further energize the magnetic field intensity of the solenoid. Magnetic flux density, magnetic field strength, that is dense means strength of the magnetic field, is represented by the vector. It is a vector quantity measured in Tesla. What I missed, yeah, this one. Magnetic flux in Weber, we can measure WB. This is the symbol named on the scientist. It is an area. Suppose that this is an area here, this is the surface of the area, and this is the normal of the surface area. Means normal means angle of the 90, and if the magnetic field is applied normal to the surface of area and making the angle 0 with this surface line, means not perpendicular but parallel to the normal to the surface area, it means that we use the cos theta, because here it angle between the normal to the surface area and the magnetic field must be 0 degree to make it maximum magnetic flux. And what area need to be considered? Definitely the area which is influenced under the magnetic field is considered, not the area which is not under the magnetic field. We are not considering that area. A conductor in a magnetic field experiences a force of magnitude F is equals to ILB sine theta, The direction of the force is given by right hand rule. And if a conductor, here a magnetic field suppose is applied inside the page by cross, and it is connected with positive and negative current, then current starts flowing through it. What is the direction of the force? It is understood that this will experience a force, either it will be on this side or this side. We can use our right hand palm rule. Our palm of the right hand will indicate the direction of the force where this conductor will move or tries to move under the influence of the current and the magnetic field applied. Basically in this is same right hand rule but different from the previous one, where we have to put tightly, and grip will indicate that where the direction of the magnetic field. That is basically the built-in magnetic field that is used for the that is used to represent here in this case built-in magnetic field of the conductor. But this one is used to right hand palm rule is used to identify the direction of the force which will be occurring on the under the influence of the external magnetic field. We are trying to ignore the internally magnetic field that is due to the flow of the current. Anyway, we already discussed this in details. The force on a moving charge particle in a magnetic field is given by F is equals to VBQ sine theta. Remember that if there is a conductor there, we connected it with positive negative. Under the influence of the magnetic field externally, it will experience a force at right 90-degree angle with the with this magnetic field. But what if the inside these particles also experience some force? If we trying to analyze the inside particles, whether they are experiencing the upside force or downside, we need to analyze these things. And in this case we have to monitor the velocity of these particles and the charge on them, either they are positively charged or negatively. But this detail already available in the last episode before the summary, I think 10. And what we have discussed already in details is the magnetic poles and dipoles, for magnetic forces, induction, magnetic fields, electromagnets, solenoid, line of the forces, and magnetic flux density, magnetic field strength, magnetic flux, and right hand rule at the end. This and much more in details is available in the previous sections. At the end of the episode 11, sorry, this is wrong, episode 11, I am trying to leave you with a very beautiful and interesting question here. A metal paper clip is not attached to an unmagnetized nail. Suppose this is a nail and I bring it closer to the paper clip, and paper clip will have no impact, shows no interest by attract or repel of the nail. It is just like has no impact if it is bring here near to the paper clip or not. Its presence will have negligence effect on it. While if I tried with a different scenario, I tries to come in with the magnet and tries to attach the nail with the magnet, although I'm not magnetizing the nail, but then if I bring closer it to the paper clip, then paper clip tries to attach it. Why? Like suppose this is the nail attached, first nail is attached with the magnet, then why second nail is attached to the first nail? Why? Same is the case. Why the paper clip is attached to the first one? So this is the end of episode 11. Further discussion will be continued in the episode 12. So take care. Allah Hafiz.